I welcome you again this NPTEL online course on earthquake geotechnical engineering. This is lecture number 43 and we are under the module 5th of this course, that is on slope stability in retaining walls. Already we have covered in we are on the first part, that is slope stability, and then we will talk about the second part, retaining walls. So, the first one, the introduction to earthquake induced landslides, we already covered. Then in the slope stability analysis, it was in two parts. One is static slope stability analysis, another is seismic slope stability analysis. So, static slope stability is already over. In fact, we have started seismic slope stability and we will continue with that in this lecture. In the seismic slope stability, we already talked about pseudostatic method, and today we are going to talk one of the new method, which is the pseudostatic analysis has been covered. So, numeric sliding and block analysis we are going to talk today, and in this influence of yield acceleration on slope displacements will be also discussed. So, numeric sliding block analysis, first what is the difference between this pseudostatic and numeric sliding block analysis, that will be discussed, and most of the stuff for this lecture is from this resource, Kramer's book on geotechnical earthquake engineering. So, it is acknowledged. Here when we talk about why we need the numeric sliding block analysis, because when you carried out the pseudostatic method, which is basically an static analysis, you repeatedly do the static analysis in pseudostatic method. So, the pseudostatic method or analysis provide you a factor of safety against slope stability, but it do not provide any information on deformation which is associated with slope failure. Now, why you need these deformations? When we talk about the serviceability of a slope after an earthquake, it will be controlled not only by the stability, but also with the deformations, and the analysis that predicts slope displacement provide more useful indication of seismic slope stability. So, one part is factor of safety, another part is on information on the deformation. So, we get both when we carried out the numeric sliding block analysis. And since earthquake induced acceleration will vary with the time, the pseudostatic factor of safety will also vary throughout an earthquake. So, the good point with the numeric sliding block analysis is that, because if you go for the rigorous analysis, then that may require finite element methods and that may be dealt using some software. However, numeric sliding block analysis can be carried out analytically, it can be carried out in the, if for the simplest case, it can be carried out even using the hand calculator or maybe Excel sheet. So, we are going to come on this one, and this numeric sliding block analysis give you the factor of safety as well as this deformations, information on the deformation. Now, if the inertial forces which act on a potential failure mass is large enough that the total means static plus dynamic which is due to earthquake or seismic, driving forces exceed the available resisting forces, in that case factor of safety will be less than 1. So, if the total stresses exceed this resistance which is available, that means demand have increased beyond capacity, in that case the factor of safety will decrease less than 1, and that once factor of safety will be less than 1, your slope is not going to be stable. So, this is one case. So, Newmark in 1965 considered the behavior of a slope under such conditions where factor of safety was less than 1, the potential failure mass is no longer in equilibrium and it will be accelerated by the unbalanced force. In that case, because once factor of safety is less, then it will not be in equilibrium. So, here what was the analogy given by this, like you have a slide which is for the potential landslide, in the figure A is shown, and you have the sliding mass, and then you have the failure surface which is could be the circular or it could be assumed some different shape, as we discussed in the last lecture. So, this potential sliding mass can be analoged with a block on an inclined plane in the second case. So, you have inclined plane or sliding block. Up to suppose in a static case, this sliding block and inclined plane, they are maybe sitting on each other, and we can in case of static case, we can find the factor of safety. So, for static static equilibrium in the inclined plane under static conditions equilibrium of the block required that the available static resisting force which is R as exceeds the static driving force dr. So, you have one side resistance of the block, another side is driving forces. So, if driving forces exceed the resisting force, then the factor of safety will be less than 1. And how for the pure, like if you have the pure sand and the resistance is due to purely frictional. So, in this case it is C equal to 0, and this condition you know that this is for pure sand. In that case, assuming C equal to 0, the factor of safety can be given by this Rs. It can be like work out like this. You have W, let us see, this is the case here. So, in this figure what you have the W? W is the weight of this block. Now, this weight of this block can be have two components, one is along the plane and another is perpendicular. So, one of the component which is in this direction and another is in this direction. So, this will try to have driving force. So, this will try to destabilize, this will try to move, but when this component will generate a reaction at the base which is equal to W cos beta. W cos beta, if I multiply by 10 phi, then you will get this frictional force between the block and plane. So, the friction force is W cos beta multiplied by 10 phi. This is your, so this whole term will be Rs and this W sin beta will be driving force. Here W cos beta is reaction, which is like that which is acting perpendicular to the plane. So, in the perpendicular direction to the plane, 10 phi, phi is friction angle between the block and plane. So, in this case what happens, because when C equal to 0, the equations is very much simplified, W cancelled out and you left out the factor of safety 10 phi or 10 beta. So, simply in this case F will be greater than 1 if phi is greater than beta. So, as long as friction angle is more than the angle of inclination of this plane beta, in that case your the factor of safety is going to be more than 1. So, no issue, but if it is less, if phi is less than beta, then the factor of safety will decrease and instability will come. So, this was all about static case. What happens in the dynamic case? In addition to the weight of this block, some horizontal force is also act, and this horizontal force act weight always act in the vertical direction, and this horizontal force, this is basically horizontal seismic force, and if you recall this was like a horizontal seismic force, you can say that this is nothing but horizontal seismic force, and this force act in the horizontal direction. Now, this horizontal force will add a component. So, now in this direction you will have two component, one is due to W which will be W cos beta, you will have this one component which will be W sin beta, and another will be plus kh into T into W cos beta. So, this will be acting in this direction and this will create your driving force which is coming down here, and on the top you will have this component W was acting this side, its component, another component will act upward. So, you will have two components, one is this side and another this side perpendicular. So, that as a result resisting force will decrease. So, in this dynamic case, when the factor of safety equation is converted here, cos beta minus kht into sin beta, tan phi and sin beta. So, here what you could see when we consider the effect of inertial forces which transmit the block by horizontal vibration and with an acceleration aht, that is what is aht? Acceleration horizontal in the horizontal direction, which is kht into g. Kht is a coefficient which is varying with the time, it is not constant because kht is not dimensionless, however it is varying with the time. So, as a result your acceleration, horizontal acceleration will also vary with the time. So, here if this equation is written by neglecting the effect of vertical acceleration is neglected here. So, at a particular time horizontal acceleration of the block will induce a horizontal inertial force which is KHW when inertial force are acting in the down slope direction, as was the case here, where it is acting in the downward direction, then the factor of safety is equation becomes here. Now, if you analyze this equation, you see the effect of KHT. If I put the KHT equal to 0, then the numerator will increase. So, the effect of KHT, this effect, it is negative in the numerator and positive in the denominator. So, as a result, the factor of safety which you find will be less than the static factor of safety. So, as a result, this effect of this horizontal force is to decrease the factor of safety. Now, suppose if you have like factor of safety in static case is more than 1, okay, then if you increase the value of KHT, then what will happen? Your factor of safety will start decreasing, and then a point will come where a factor of safety becomes 1. And if I put factor of safety equal to 1 in this equation and solve this equation, then I get a relationship, very simple relation, which is for KH. What is KY? KY is nothing but KY is the value of KHT for when the factor of safety becomes 1. And in this equation, last equation, if you put 1, that means numerator and denominator should be equal, and replace KHT with KY, then you solve, then you once you solve, then you find tan phi minus tan beta, which is basically nothing but tan phi minus tan beta 1 plus tan phi tan beta, tan phi tan beta. So, this way you find, and this KY is called yield coefficient. Dynamic factor of safety decreases. So, the dynamic factor of safety will decrease in this equation when KH increases, and there will be a value of like when how much we should increase the value of KH. If we increase the value of KH to a point where your factor of safety becomes 1, in that case this coefficient will be termed as the yield coefficient KY, and this yield coefficient KY will be corresponding to the yield acceleration, which is given by AY is nothing but KY multiplied by G. This is a minimum pseudostatic acceleration which is required to produce instability of the block for sliding in the downslope direction. So, KY will be tan phi minus tan beta, tan phi minus beta. Here in this figure, you see that like there is slope with beta equal to 20 degree. There is a slope in this case, beta equal to 20 degree. Now, in this case, the factor of safety what is the value of KH where the factor of safety becomes 1. For example, like this curve is for 20 degree when phi equal to 20 degree. Naturally, when phi and beta are equal, then factor of safety will become 1 even when KH equal to 0. So, the factor of safety 1 when KH equal to 0. But if you increase the value of phi to 30 degree or 40 degree, when KH equal to 0, your basically KH equal to 0 means this is for basically this is belong to static case. This is static factor of safety. So, the static factor of safety will be 1 here. When phi equal to 30 degree, it will be more than 1.5. When 40 degree, it will be more than 2.5. And when the KH increases, the factor of safety start decreasing. So, here in phi equal to 20 degree, it will start decreasing and become less than 1. But for phi equal to 30 degree, there will be a point, this line is for factor of safety equal to 1, where the factor of safety becomes 1, and this point is nothing but 0.17. So, this value is 0.17, and this is for phi 30 degree. Similarly, for phi equal to 40 degree, this is 0.36. So, naturally the value of KH will depends on your two things. One is the angle of inclination beta, and another is your phi, which is angle of internal friction. So, if phi is higher, then you can have the KH higher value where the factor of safety will be 1. If it is low, then in that case even at low value of KH, the factor of safety will becomes 1. So, this was all about that. When a block on inclined plane is subjected to a pulse of acceleration that exceeds the yield acceleration, then in that case the block will move relative to the plane. And how it the movement? Let us consider the case in which an inclined plane is subjected to a single rectangular acceleration pulse of amplitude a and duration delta t, which is shown in the slide, and we will be using this slide frequently to explain. What is in this case? Let us discuss the acceleration part only right now. Acceleration, rather than a times tree, we are using a pulse, rectangular pulse. In the rectangular pulse, maximum value of the acceleration is capital A, while duration is, this is t naught and this is, so this duration is simply here to here is, this duration is delta t. So, this pulse have total duration delta t, and in this case, because A, this maximum value of A is greater than Ay, that is why yield acceleration, because in that case the permanent displacement will develop. Here single rectangular pulse, A and duration delta t, and the condition is here A is greater than Ay, yield more than yield acceleration. If it is less than yield acceleration, in that case there will be no movement, because so the condition is that A should be greater than Ay. Now in this case yield acceleration Ay, or other way we say the Ay is less than A, the acceleration of the block relative to the plane during the period from t0 to t0 plus delta t, during this interval you have A relative t, which is given by ABT. What is ABT? ABT is nothing but base acceleration, which is varying with the time, and Ay is yield acceleration. The maximum value of ABT is constant. Here during this interval, during this delta t period, your acceleration is not changing, it is constant at the A, capital A. So, the difference will be A minus Ay, and this is applicable only in this period t naught to this one. So, what we do, if suppose this is a excess acceleration, so this you can treat like this one, the difference of the acceleration, maximum value minus the this yield acceleration. So, this is excess acceleration, and if we integrate this one, then you will find the velocity. If you integrate once more, then you will find the displacement. So, where the relative movement or block during can be obtained integrating the relative acceleration twice. So, it has been done here. So, whatever we find out in the last slide, so if I integrate it by once with the time, then I get the relative velocity with the time. So, this is give you again, if I put in the relative velocity here, integrate once again, then you find the relative displacement, and here both relative density velocity and relative displacement both are function of time, that means they are varying with the time. Now what will happen, as a result relative velocity, because acceleration is constant here, acceleration is constant as shown here in the slide, as a result your velocity will linear, be increasing from this time to this time, because and the velocity will become maximum at t equal to t naught plus delta t. Why? Because after that acceleration stops and it becomes 0. So, up to this point velocity will reach to maximum point. And so, what you can do, you can find this velocity by integration, and you can find the displacement up to this point. So, this has been done. Another issue, after this you have acceleration stops, there is no acceleration after this point in this case, but there is yield acceleration. So, the relative will be minus Ay, the difference Ay, this difference between then this one was positive. When this A becomes 0 here and this is, then it difference will become negative. So, that we are going to work on that. So, using that deceleration, so between from this point to this point there is deceleration. So, the velocity first will reach to the maximum value, and after the, because then there is a deceleration rather than 0 acceleration. So, as a result velocity will decrease and will reach to a value 0, which is the velocity becomes 0 at time t equal to t1, and then you integrate, then again you find the displacement here, and the displacement become constant after this point, this is maximum value of this one. So, how it is done? So, we already find the values at this, you can this is the equation for velocity at time t. If I put t minus t naught equal to delta t, then I can find the velocity at this point, and so this is the at delta t time, this is given here, this is the velocity at the there, and the displacement. So, these values represent the values at this point here as well as here. Now, after this there will be a deceleration as we discuss after time t equal to later, and this deceleration will be base acceleration minus a y. So, it will be 0 minus a y. So, that means it will be negative acceleration minus a y, and with this negative acceleration t0 plus delta t, and this will be applicable in a time period after t0 plus delta t, but less than t1. How we can find the value of t1? T1 can be found out. T1 is the point where your velocity becomes 0. So, here you have got the, you know, the maximum value, and the maximum value after time with the given acceleration where your velocity becomes 0. So, using this can be found out the relative velocity will decrease with time according to this, and if using this expression, if on the left hand side I put velocity equal to 0 and solve this equation, then t whatever you get t from this equation will be t1. So, you can obtain the value of t1 from this one. So, t1 is obtained, this is the answer here, t1 is obtained. So, now you know everything here, this point is known, this time is known, and then we can do this once more the integration of this equation between this time period, and the integration will give you the displacement. So, we find the displacement, and this displacement is between t0 plus delta t and t1. At time t1 the block and inclined plane, now at this time t1, what is the condition at time t1? You do not have any acceleration, you get stopped here and no deceleration, nothing. As a result, the block and this plane, they will be moving together, there will be no relative displacement, the block and inclined plane move together during the total period of time between t equal to t naught and t equal to t1. The relative moment of block is shown as here. So, this was about. So, this way we can find ultimately what is our objective doing this all this, we find this value because which is the permanent displacement. So, this value becomes constant from here to here, and your objective is to find this value for, and which is the maximum value of the displacement, and that displacement, maximum value of displacement is used further in design. So, between t0 the relative velocity increases linearly, and between t0 and t0 plus delta t thus, and the relative displacement quadratically at t0 plus delta t has reached maximum value, which we already discussed, and these values at t equal to t1, this is given. So, this gives you the using this equation at t1 you find the displacement which is the maximum value. So, this displacement is at this point. So, this equation give, and naturally this will not be depend on time because this time is fixed, t1 is fixed. So, as a result this value is also fixed. So, this way you can find the maximum value of displacement using this expression, and this depends. So, naturally this depends on what? Ay is yield acceleration, which depends on your material property, which is we already discussed how to find the value of Ay. Ay can be calculated simply ky into g. What is ky? Ky is nothing but tan phi minus beta. So, what is phi? Phi is the angle of internal friction. What is beta? Beta is your this slope angle. So, that means we know the Ay that depends on your geometry and the properties, material property. Now, this relative displacement will depends on other two factor. One factor is A and another factor is delta t. Delta t is the time interval of your pulse, that will depends on your frequency of excitation, and A is amplitude. So, the total relative displacement strongly depends on the amount with the length of time during which the yield acceleration is exceeded, number one, that is delta t, and the second thing its amplitude. Relative displacement caused by single pulse of should be related to both the amplitude and frequency content, this is the case. Thus, so this was regarding Newmark sliding block analysis. Now, before we will discuss one example on Newmark sliding block analysis later, but before that, what is the influence of yield acceleration on slope displacement? First we will discuss using the Newmark sliding block method, and then later with some other method. The sliding block model will predict 0 permanent slope displacement if earthquake induced acceleration never exceed the yield acceleration. So, if your Ay or Amax is greater than 1, that means your yield acceleration is greater than Amax. Amax is the maximum value, or you can say PGA, which you may expect during in an earthquake time history. If your yield acceleration is more than that, then there will be no permanent slope displacement, and you do not require any further analysis. However, if your AY yield acceleration is less than Amax, then you require. Since the permanent displacement is obtained by double integration, the computed displacement for a slope of a relatively low yield acceleration. So, as much the difference between AY and Amax, if difference is large, you can expect that permanent displacement will be more. If this is less, in case of, because let us say in a given earthquake, I fix the value of Amax. So, if my AY is low yield acceleration compared to Amax, in that case you will get more higher values of permanent displacement, but in case of your AY is higher, then you will get less. So, which has been explained here. So, what you see here in the first figure A, you have maximum value which is just touching AY, that means difference between AI and Amax is 0. So, no permanent displacement will be developed. Then, so in the second case, value of AY decreases, yield acceleration is here, this remains as it is. So, this will create, because during this interval your acceleration have exceeded the yield acceleration, and it will create the permanent displacement. Further AY decreases and you got these peaks here as well as here. So, that means permanent displacement was 0 in case A, then it increases, and then in case of C it further increases. Now, coming to the Newmark also demonstrated that maximum permanent displacement, which we say Dmax, which is produced by an earthquake motion, is given by the relation Dmax, in this case, in this relation Vmax square divided by 2 AY Amax for, and in this case this expression which give you the maximum value of displacement using this expression will be valid provided that the value of AY by Amax is equal to or greater than 0.17. So, before we use this expression, we need to make sure that the value of this ratio yield acceleration to is greater than 0.17, and naturally when EY is greater than 0.17, that means even it is not greater than 1, that means in this case yield acceleration is less than the maximum PGA. So, in that case factor of safety will be more than 1, but what happens, like you have yielding is started, then still it will create some maximum permanent displacement during over the time of earthquake. So, where Amax and Vmax are the, and what is Vmax and Amax? Maximum acceleration, peak base velocity due to earthquake excitation respectively. AY is the yield acceleration. So, with this we continue. Now, there are some other researchers also who like try to estimate permanent displacement using the value of yield acceleration AY by Amax, and one of them Ambrasis and Minu in 1988 suggested that permanent displacement in centimeter, this equation is not dimensionless. If you find out from this then you will find the displacement, because this term is coming 0.90 and it carries some unit. So, the answer which you find from this u, which you will be finding, it is log scale and log u. So, then you whatever you find u, it will come in centimeter. So, by actual ground motion for a small, and this will be applicable when AY by Amax is small. If it is quite large, then it will not be applicable, and this equation have a standard deviation sigma log u equal to 0.30. So, in this equation you have AY by Amax and this powers and the 0.9, and this equation is will be applicable as we said for the in the range AY by Amax should lie between 0.1 to 0.9 to application for this. Then this equation is applicable for the magnitude, surface magnitude of earthquake between 6.6 to 7.3, and AY is computed using residual solid strength. This was by Ambrasis and Minu. Similarly, Youngin et al. In 1991 developed the following expression for the which also in this last equation you have only AY by Amax one parameter, but in this case you have NEQ, which is number of cycles of earthquake, and time period also involved here. And in this case you have this but the issue is in this case is in this equation u is coming on the right hand side also. So, you need to do the you need to work it here in this is log u star. So, u star is a dimensionless, which is u divided by a max n e q t square. So, on the right hand side you have a y by a max, and again here because this unit is coming. So, this is also in centimeter. So, this equation is also not dimensionless, rather it is have some unit, and the standard deviation is given here. So, what do you do? Using this equation you find on the right hand side, okay, but here because this is okay, this is dimensionless, because this you find ultimately this ratio. So, once you find this ratio, then you find out this value, and once this value is known, then you can find out the u value of u equal to a max n e q into t square, where n e q is an equivalent number of cycles and t is the predominant period of the input motion. Gibson also suggested correlated sliding block displacement with the area's intensity, and using the area's intensity, which is in IA in meter per second and AY in G, and in that case using this expression the permanent displacement can be found. The answer comes which you get is u is in centimeter. Two aspects of seismic slope stability are clearly illustrated by these studies. First is earthquake induced slope displacements are very sensitive to the value of the yield acceleration. Consequently, small difference in yield acceleration can produce large variations in predicted slope displacement. So, if you have a small variation, then there will be displacement, there will be large variation in the, because it is ultimately difference between your maximum value of acceleration minus the yield acceleration. So, if it is the difference is large, then you will get the large displacement. The second, the great variability of distribution of acceleration pulse amplitude between different ground motion produce great variability in predicted slope displacement. So, if you have the large variability, then the variation in the slope displacement will be also large. Even ground motions with similar amplitudes, frequency content and duration can produce significantly different predicted slope displacement. The uncertainty must be recognized in the prediction of earthquake induced slope deformations. Coming to this one example, a small example on Newmark sliding block analysis. Here the peak values, peak acceleration A max is given to you as a 0.442 g, and peak velocity V max is 33.7 centimeter per second. And one more information is given in the question, which is yield acceleration 0.112 g. So, first thing what you do, you find the ratio of AY by A max. AY is this one 0.1124 and A max is 0.442, and this ratio comes out to be 0.2543. So, this is more than 0.17. So, this is okay. As a result, we can use the equation which is given by the Newmark here, V max. So, just what we do, we put the numbers here. AY is given you yield acceleration 0.1124 g, and the value of AY, if I put the value of g 98.1 centimeter per second square and A max by A. So, all the numbers are put, and then finally D max you should find is about 20.25 centimeter is the displacement, which is maximum permanent displacement, upper bound estimate of the permanent displacement using Newmark sliding block analysis. So, this was all about Newmark sliding block analysis as well as the influence of the input parameter. Thank you very much for your kind attention.